So good afternoon, I'm Alessio Guerrieri, and after following a lot of presentation these few days, I understand that I don't understand machine learning basically. That's my conclusion, because I know how the concept behind machine learning, I know how the different components work, how they fit all together, and how to change the parameters and how to fit them in a way that helps the model grow. To me, it's basically still a mystery. I try to change stuff. I try to not overfit on our small training data, but I still treat it mostly as a black box. And this is something that I think I'm not alone, because it's pretty well known that machine learning models are black boxes, basically. But it is highly dangerous. So this presentation is about this problem. I will start with a couple of examples. So this was from a paper that's trying to show how not understanding the explanation of a model can be harmful. This is a husky. They trained a model to classify huskies and wolves, and they found that this was a mistake. So this was a husky classified as a wolf. Nothing weird here, because I mean, all machine learning models make mistakes. But then if you have a look at why the mistakes was made, they found that the reason was this one. Basically, it was looking if there was snow in the background or not. That's how the machine learning model, the highly complex machine learning model, was working. So it's a machine learning model that maybe it's precise often, but it's very easy to fake. Another example, many of you know these slides. You can do embedding of words, and then you have arithmetic on the words and relations between them, so that the relation between king and queen is the same as the relation between man and woman, and there are a lot of other relations that you can get from embeddings. But you can find that maybe if you train the data, you don't look at the model, you just trust that what you get is nice. You find nice relations such as this one, but you also find relations such as this one. This was found in a machine learning model that was trained. So maybe you don't care about this, the fact that you say man is to computer programmer such as woman is to homemaker, but it is an issue. If maybe you don't care about it, but maybe you're selling this model to someone else, you're doing it for a client, and maybe the clients care about this. They worry about the public perception of this result. So this presentation will talk about these issues and how we tackle them. We use tools that are already available to tackle these issues. So I will introduce the reason because we are worrying about machine learning interpretability, the different techniques that are available for the different types of models that we use. We tend to use simple models, so you will not see rocket science here. And then I will introduce Shap, which is a Python library that is very easy to use and very powerful, that can help you interpret your machine learning models. So start from introduction. This is me. So as I said, I'm a data scientist at Spazio Dati, and I do a lot of geeky stuff in Trento. So I'm part of a group that does board games, and I do teach and a lot of stuff. Most all of them geeky, basically. So. And this is us. This is Spazio Dati. These are the. It's a photo from this December. We were a startup until a couple of years ago. Now we are too old to be a startup. We are part of a bigger group. It's called Cerved, and we are based in Trento and Pisa. What you need to understand to get the rest of the talk is that what we do is basically take data from different sources. Some mostly data about companies. Some come from the Chamber of Commerce. So they're official data such as balance sheets, number of employees, and so on. And some we get from unstructured data such as the web and the news and those kind of things. We put them all together. We serve them as a web application / search engine / database / whatever. And also we use it for specific projects. So big clients come to us with their data about their customers, and they ask us to do some machine learning things. I will not go into the actual problem that we're trying to solve, but the idea is that they have some information about their clients, and they want to compute a score that either find if that company is in good shape, or maybe find companies similar to other companies, and this kind of models. So it's mostly prediction and scores and estimation. And this is just sales kind of figure that shows us what we do. So why do we need explaining for our machine learning models? So I'll present a couple of our use cases. The first one, the most important one, is since we're working with big clients, we need to be able to explain what we do to these clients. And we can explain them the algorithms behind it, maybe. Probably not a good idea since they don't care at all about the algorithm. They care about the results and they care about the model. But what we want to show is not only that the numbers are good, so that the metrics are good, but also that they make sense. That for a human, they make sense. They want to be explained stuff so that a human can understand it. And therefore, we need to tell them what are the important features, how they talk to each other, which of their features that they sent us are more important, and how we use them in a way that they can understand without being technical people. The other use case is more specific, is single prediction. So explaining not the model, but how a model predicted a single value. So what we do mostly in most of the cases is predict some kind of score, some score that can be a probability of an event, or it can be a similarity with respect to a group of companies. And that can be seen just as a number. And if it is just a number, it means that when the human operators, the human users will take that number, they will not be able to understand what's behind it. And they basically, at the first time that it will be wrong, and it will be wrong because we make mistakes, machine learning models make mistakes, they will stop, they will start losing trust in the model. If with the score we also can give them some kind of explanation of what are the features that impacted that specific prediction, then everything becomes much easier. It's easier for them to use the model to understand when it's wrong, why it was wrong, but also to then continue trusting the model. It's much more powerful for most of our use cases to have a model that is explainable than a model that is more precise. Because anyhow, there will be a human user at the end of the process. And finally, which is something that is very helpful, is debugging. So it happened a couple of times to us. Once we found that a model was performing amazingly, we went a bit deeper to understand why, and we were basically cheating. We were using features from after the event instead of before. Some simple bug, but if we didn't find it, then the model we could have sold the model as amazing, and instead it would have been completely crappy. But also in a more practical scenario in which we trained a model for a client, we prepared everything, it was fine. We went, okay, let's go into production. Let's double check the model, and we found that in the last stage of putting into production the model, we trained on the wrong CSV file. And so the model didn't make sense. And so stop the line, stop everything, ask the client to wait a couple more days, and then we need to retrain the model. If we treated the model just as black box, we wouldn't be able to understand when there is a bug and when there is something that doesn't make sense. And I didn't do the mistake, but yes. But I didn't fix it, so. So solutions, what can we do in practice? So for this presentation, I took a dataset from Kaggle to have some examples and so that we can see some explanations. I took a dataset of movies. I didn't put the link in the slides, but I will put it because I forgot. And there is a bunch of movies and some characteristics about the movies, and we're trying to predict how much money that movie made when it was put into the theaters. Clearly, this is data from a long period of time, so there are huge errors here. There are a lot of correlation. We are doing an extremely crappy job here as data scientists because clearly we are using the number of votes on IMDb to predict how much money they made in a theater, which is clearly something that you cannot do if you want to predict in advance. But that is not the objective of this talk. And anyhow, I don't know how to do machine learning, so who cares? So, and I chose a couple of movies for which we can see the explanation. So, Jurassic Park, Schindler's List, and Monty Python and the Holy Grail. So, a comedy, and a drama, and an awesome movie. So that we are all happy. The first model that we can see that sometimes we don't think about it too much is linear regression. So simply you take the features and you compute a weight for each features, and then you have a linear formula to estimate the score. It's this maybe the simplest machine learning model that you can use. Sometimes it's pretty useful, and if it can get good results, you should think before moving to more complex models, because this is extremely easy to explain, because the formula is a formula, and you can just take the weights and understand which are the ones that are high positive correlation, negative correlation. It's very simple. If you look at the one that has the most weights, actually the results are pretty weird. You have a bunch of foreign language, and that's negative, another bunch of foreign languages, and science fiction, which is negative, and it will be negative for the rest of this presentation. I'm sorry, I'm sad, but yeah. Because this just looks at the weight, so even if a feature is not present very often, it will stay here. But if you look at the specific instances, a specific item that we're trying to predict and understand how the features interact, then you get something that makes more sense. So you see that for Jurassic Park, the number of votes and the budget has a positive impact on the prediction of the model, while the average vote and the genre science fiction is negative. You can easily understand, and the good thing about this kind of explanation is that it's exactly what the model is doing. So you explain exactly what the model is doing, is precise. There is no risk of having the explanation and the prediction clash between each other. Obviously, it's still a linear regression, so if you want to do something complex, you either do a lot of work in pre-processing of the features, and there are some nice talks you can find online about using linear regression for very complex topics, but still you might want to move a bit forward and try to use more complex models. So the next one, the decision trees. This decision tree, very simple. You have nodes in which you select which way to go, and for each item you find out where it falls. So how do you understand the prediction of a decision tree? Well, you can do it pretty easily. Well, you can ask for the most important features in general of the model, looking at the one that contributed the most at the spread of the entropy, I think. I don't know if entropy is the correct word, but. And you find that these are the most important features. They make sense. So actually, animation and adventure seem to be very important. You don't understand very easily if it has a positive or a negative correlation. So you understand that these are important. You don't really know in which direction. You can get it, but you need to do a lot more work than what we're doing right now. And if you want to understand a specific prediction, you can have a look at the path that the prediction took into the tree and understand which features it used. So you know, for example, that for the prediction of Schindler's List, it didn't use the average vote or the release month or all this kind of information. They weren't just used. And you don't really understand in which direction it goes. So it's not very easy. And since you're already in the realm of models that are not that easy to explain immediately, you probably don't stop a decision tree. I don't know many use cases in which you stop a decision tree without going to what we mostly use in our company, which is random forests or gradient boosted machines. So forests of trees. Actually, in what we do, we mostly stop here as far as complexity of the model. We don't tend to use much neural networks because we don't have much training data. And so in our application with mostly categorical features, and features that are not present in the same amount, we have a lot of none, a lot of information missing. This is the kind of model that works the best, the most complex kind of model that works well. So how do you explain a prediction with random forest and XGBoost? It's actually pretty complex. So you can ask him what are the important features, and it will give you something that makes sense, usually. Also here, it's different from what you got for the decision tree, but the decision tree is one, and these are many. But the algorithm is basically the same. So you see there are the 4 main features that are present everywhere, and a couple of specific features that seem to be important for it. But so this is something that we were still using when we were using since before I went to Spazio Dati. Actually, we were starting using these kind of models. But without worrying about the explanations. Now we want explanation because the clients are really asking us for it. How do we do? Well, we studied what is the state of the art. We don't have time to actually invent our own techniques, so we try to use whatever is available, whatever has been already implemented, and it's out there in the open source community. So there are different options. One option that is very common is surrogate models. The idea behind surrogate models is that you train your model, whatever the algorithm is. You can, so your model could be random forest, could be candidate boosting. It did something that I didn't expect it to do, but we will get it back, hopefully. No, everything is black. Nice. Okay, for now I'll take this one. I don't know what's happening there. So you can use whatever model you want. It could be even a neural network. You get a prediction, and then you use a surrogate model, which is another model, simpler than the one that we had before, something that you are able to explain, a linear regression or a decision tree or something extremely simple. You see on the prediction, and you use an explanation, and you try to explain that model. So from the data, you train a model, you get a prediction, you train the surrogate on the prediction, and try to explain the surrogate. The surrogate is much easier to predict, and therefore you are able to get explanations. You train the surrogate on the prediction and not on the actual value that you're training on, because this way the prediction and the explanation are much closer related to the other. So they can live together, and it's less likely that the explanation and the prediction will clash. Still, this is dangerous, because obviously the surrogate model and the old model are trained separately, and so they can clash. They can give you different results. And if a client sees a prediction of a very negative scores, and all the features have positive correlations, they will see, okay, this is something wrong, this model is crap, let's throw it away. So even if there are few cases in which the prediction and explanation clash, it's very dangerous to keep them. Now let's see if okay, now it worked. Good. So the next technique that you can use is LOCO, leave one covariate out, which is a complex term for something quite simple. You want to estimate what is the impact of a specific feature on a prediction. You take it away and see how much it changed. That's the gist of it, actually. It's a very simple approach. So you have your features. I shouldn't click on this button. I think I'm finding the reason for this thing. Sorry again. At least I know now. So you have a bunch of features. You have the prediction. You try to take out a feature and see how much it changed. You take out the second feature and see how much it changed. And you do it for each different features. And therefore, you can measure the impact of each feature on each specific prediction. It's maybe a bit simplistic, but it has the advantage that it is completely model agnostic. So whatever model you trained, you can use this approach. And you can get something that is usually meaningful. Maybe it's not complete, but it's meaningful. So if you have a look at our usual free movies, you get something that can make sense. You can actually show this to a client, and they will not find huge issues with it. One thing that I would like to point out without using the pointers is the fact that for Monty Python The Holy Grail, the fact that it's an adventure movie is a negative, while for Jurassic Park, the fact that it's a positive, the same feature. The same exact feature, the same fact is used as a negative and a positive on different examples. Now, this is expected, and it's something that we actually want on complex models, because it makes, in this case, the explanation that I will give is that for adventures movie, if they have very low budget, it's unlikely they will do much money. But if you have a huge budget and you are an adventure movie, you'll probably do a lot of money. That's my explanation. So it makes sense. But if you show this to clients that are not used to models that are more complex than linear regressions, so that maybe they come from a more statistical background, and using statistical improperly, probably. But this is something that you need to be prepared to explain. same feature, exact same value, different contribution to a prediction. It happens. Now, Shapley. We reach finally the actual tool that we are using now. So we tried experimenting with different tools, but this is the one which we chose. Shap comes from, the name comes from the Shapley additive explanation. It's one of those weird kind of acronym. It's based on mostly game theory. So there is the Shapley values that come from game theory, in which you have a number of contributors to some kind of game, and you need to divide the reward in a way that makes sense for the contribution of the different players. And there are variations to allow for coalitions. There is a huge amount of work being done in game theory about these kind of values. And the idea behind this tool is that they took the definition from game theory. They tried to take ideas from different approaches, such as Lime and a few others, and try to find a distribution of contribution to the features such that they follow specific requirements from the original game theory definition. So that they should be, the sum of the contribution of the features should be exactly equal to the prediction. This is one requirement that you also want to know. They want the contribution of the feature to be consistent with the actual model, of how the model works. To want to be consistent also, meaning that if you remove, no, that is missingness, okay. No, missingness is if you remove a feature, the absence of a feature is not an indication in positive or negative in general, unless something is going wrong, but that it should be neutral, and consistency, meaning that if you increase the contribution of a feature, the reward should also increase. It shouldn't go in different directions. It should be consistent by itself. How do you use Shap? Shap is the advantage of Shap. The main reason why we use it, actually, is it's extremely easy for us. It's very simple. So you import it, you install it via pip, and then you have a model. You just create an explainer. An explainer is an algorithm that looks at the model and tries to guess how to distribute the weight of the features. There are different explainers. The one on the top is a tree explainer, meaning that it can be used for decision tree, random forest, XGBoost, and it's optimized for those kind of models. It's actually very fast, and this is the one that we use most cases because we tend to use those kind of models. But if you have a generic model, it will still try to work using a kernel explainer and some other kind of algorithms that still try to distribute the contribution in a way that makes sense. And once you have the explainer, you just give it the input, the input features, and it will compute the contribution of the different features. So the key part is that the explainer is by itself a kind of model that tries to generate the prediction. So it's not a simple list of weights to give to the features, but it's really an algorithm that is built based on the model. Once you have this, you basically are finished, because in Shap values you have for each input, for each feature, the contribution. Very nice, very clean. Then you can do whatever you want with it. For us, since we use it very heavily during the development to understand the model we are creating, to debug and to decide how to proceed, if we need to add new features, if we need to look for new data, then it's a bit, we use it inside the Jupyter mostly to really see. It's because they have a lot of very nice visualization that we'll see, and hopefully you will be able to see even from the bottom, but some will not be able. So one thing that you can do that is extremely helpful is a summary plot. So you just do summary plot, you give it the values, the input, you tell it how many features to display, and it will do this nice explanation. So what it is, these are the 10 most important features. It will show you, according to the feature value, if it is low or high, if they have a positive or negative impact on the prediction. That's the X, that's the Y. So if you see vote count, which is the most important feature in every model, if it is high, it has a very positive, contribution to the prediction. So this is according to the prediction of the model. So we learn very easily from this one that what counts, the more is better, which is obvious maybe, but with most other models to actually get this insight, you take a long time. Here you just write this one, you get a nice figure, and at a glance you can see some patterns. For example, the fact that family movies tend to have being a family movie, tend to have a positive contribution according to this model. Here we are only talking about describing the model, not describing the actual data or the reality. Just keep in mind that this is a crappy model. Science fiction, as we said, is as a negative, adventure is positive, romance is positive. Budget is a bit mixed, tends to be positive, but there are also some very, there are also cases with a very high budget, you can see it there because there are some red points on the left, in which it has a negative contribution. So the model decided that even if, no, because the budget is very high, then you should give a penalty to the prediction. This, for me, is one of the most important features that Shap give you. So a nice dashboard in which you can understand how the model works in general. Then you can go a bit deeper into specific features. Now here you have the value of budget on the X, the budget of the movie. On the Y, the contribution of the budget. And it's colored blue or red according if it is or not a family movie. Clearly, you can change these things. It's all in one line of code. It's very easy. And you can get some information here. You can see clearly the relation between budget and the contribution of budget, meaning that you can now explain that the model, what it's doing is giving, considering budget a positive thing to predict how much money the movie will make. But also you can start seeing that maybe for family movies, this correlation is even stronger. It's a bit higher probably. You cannot really get it from here. Probably you want to go a bit deeper, and then, but you can easily do some normal NumPy pandas thing, create a mask so that we are looking only at the samples that are family movies, and see the same plot, so budget, contribution of budget for only family movies, and see if the comedy gives an effect or not. And you can see that the relation is pretty clear. And again, this is the contribution. This is going into the model, not in the data. So we are able to understand. You're able then to explain to the client what the model is doing. This is the most complex kind of visualization, which is the force plot. This is an interactive JavaScript kind of thing in Jupyter, meaning that you can actually click on the buttons in Jupyter and it will change. You can select what you have on the X and on the Y. You can select the contribution of the, so here it's showing the output and it's output of the model, and it ordered the samples by budget. So that on the left there are the one that with the lowest budget, on the right the one with the most budget, and you can see how it grows. I personally never found this useful, but other people actually, other colleagues used it, so I guess I can just tell you that it's cool because you can click on stuff, and I'm still not used to click on stuff in Jupyter. So I saw some presentation done with Jupyter at this conference, and I was, wow, amazing. And then finally, what is the main usage that we do? Explaining a specific prediction. It gives you a nice visualization. You probably cannot see the words on back, but I will just give you here an example. You have a Jurassic Park on the top, and you can see for each feature what count. If it's an adventure movie, it's released in June, it has a big budget, how much they contributed the prediction in a positive direction, and how much the different features, such as the fact you cannot read it, but such as the fact that it's not a family, it's not a family movie according to this data. Right? I don't know. I saw it when I was 10 years old, so I don't agree. But it has very few features that have negative impact. You can see Schindler's List here. The budget has a negative impact. So you can see how much, visibly, you can see how much it brought the prediction left, so lower. And you can see all the other features. And then Monty Python, the highly gray, which has clearly the lowest prediction, which as it should be, being a cult movie. And you can see which features contributed. The fact that runtime is very low, the fact that the budget is very, very low. As if you've seen it, you know it. And but still, it has a lot of votes, so that still gave a good contribution. And actually, according to the model, these few votes still had a very good contribution with respect to this one. Now, as I said, we mostly work with categorical data, numerical data, so I don't have very much experience, stuff to show you about text recognition and the neural networks, so I didn't produce much about it. I just want to show you some of the examples that Shap shows on their main page. So if you do simple digit recognition, you can still ask him what are the features that contributed the most to a prediction, with the usual rule that the sum of the contribution of the features is the prediction, which is very helpful, and you find something that makes more sense than 2 and 1. Interesting with 0, the most important part is the fact that there is empty inside. There is a hole inside. And for 4, it's very important the fact that there is an empty space on top, because otherwise it will be 9. So for them, that has a very strong correlation. The fact that this is empty is very important for it being classified as a 4. But you can find other examples. Here, this is another example that showed the important part to understand specific animals. For a meerkat, the important parts are the eyes, those dark eyes, those creepy eyes. And for the dewitcher, which is a kind of bird, is mostly the beak. On the website of Shapley, you can find a lot of notebooks that have already been implemented with examples coming from different fields. So I will recommend you to have a look at that. As you've seen, the amount of code needed to use it is very, very minimal. So it's very easy to play with it if you have any kind of model and try to understand how it works and try to go a bit deeper in how it behaves. So I will conclude briefly with some takeaways, I hope, from this presentation. The first one, which is, to me, is very important. If you use a simple model, then the work is much easier. It's much easier to understand a simple model. And that is an important thing for a model. Precision is not the crucial part when the eventual user of your model is a human that will likely want to understand what's going on. And so the more complex you become the model, maybe the better the prediction becomes, but the less accurate can become the explanation. You need to be very careful to make sure that your explanation is consistent with your prediction. Otherwise, if they diverge, you can lose the trust of your customer, and the user will stop using that kind of approach. And hopefully, I show you that Shapley is very easy to use. It's a couple of lines of code, and it has a lot of work behind it. It's actually the combination of a work of, I think, 6 different approaches that have been brought together in a common framework. It uses a lot of, there are a lot of interesting papers about this approach. So it's not just easy to use, it's also very, very good at what it does. And in our experience, that is what happened in practice. So showing this kind of explanation again made the value of our model become that much higher. So yeah, that's all. Thank you.
As always, if you have some questions, we have 5 minutes. Okay.
Thanks for the talk. It was very interesting in many ways. But you mentioned that obviously the model makes a simpler model is easier to explain. Do you have any observations on whether simplifications in the data would make the explanation simpler? So, for example, reducing the number of features, or maybe reducing the ranges of the different features, domains, sorry.
Well, sometimes doing some work on the features can help you use a simpler model on one side. That is something If you do some bit more work than just taking the numbers, you can actually use linear regression for stuff that is not standard. But in general, it's difficult for our use cases to actually remove features, because we have a wide variety of features. They come from really completely, it could be stuff such as the revenue of a company is pretty high, but also they have a Facebook account. So they are so different that you never know exactly in advance what you can remove. And therefore, you can do some simplification afterwards. So after the model has been trained, you understand which features are important, and then you redo everything by first removing some of the features. But sometimes model changes unexpectedly in our experience. And so we tend to just leave it there and then do some cleaning on the explanation, maybe. So the explanation, we only show the explanation for the feature for which we want the user to know they are insignificant. If you know, we do the other way around.
Hi, thank you very much for this presentation. I was wondering how costly is it to train these explainer objects, for example, for XGBoost algorithm?
So, considering that our models are pretty small, so the total amount of companies that are in Italy active are 6 million, so we never have more than 6 million data points. We mostly can do everything on that laptop. So getting the explanation takes longer, sometimes than training the model, but we are talking minutes, not hours. But the amount of data is small, so if you have a lot more data, I would expect to be a bit more than training an XGBoost model, if you don't do too much work with ensembles and those kind of things.
Other questions? We have 3 minutes left. Okay. So thank you, and I think we are going to see the other talk. So thank you for being here and for the talk.
Thank you.